binomial, couldn't we actually map out the probability distribution and find the probability that x is equal to 0, the probability x equals 1, the probability x equals 2, so on and so forth. So can everybody pick like one, and don't everybody pick the first one, and don't everybody pick the last one? You guys know what I'm saying? What's the probability that you guys pick all 5? I think it's pretty high. Can you guys help me fill in this probability table? What would we use in our calculator? Binom PDF. And n would equal?
2 is 0.91.
Thank you.
0 is 0.005.
1 is 0.048.
3 is 0.336.
5 is 0.116. 4 is 1.332.
It feels close. Something feels a little... That could be because of rounding. Okay. All right. And because it is binomial, can we find the mean of this and the standard deviation of this? Uh, 3.125. Is that just 3.25? And 1.09. I'm doing that from memory. Is that close? 1.067. Great. Okay, thank you. All right. Now, you guys, if 2 people said yes, could we turn that into a p-hat? Yeah. If we had 2 out of 5 people in our sample, how could we turn 2 into a p-hat? We would divide it by 5. And in fact, couldn't we turn each and every one of these into a p-hat by dividing by 5? Very good? Now, last unit we talked about like transforming. If I divide every single value in my random variable by 5, what's going to happen to my mean? It's going to be divided by 5. What about my standard deviation? It's going to be divided by 5. So, to find the mean of the p-hats, I just take my 3.25 and divide it by 5. Guess what it is? 0.65. Is anybody shocked by that?
No, because we multiplied by 5.
Okay, so here's the deal. No matter what's going on with my binomial distribution and my p-hat distribution, okay, all the p-hats can be described as binomial, just like our starburst. We could have easily done this 0, 1, 2, 3, 4, 5, 8, 7, and 6. 2. In the past, I've done 5 starbursts, but you guys, I gave you more. Okay. All right, and so here's what happens. In the same way that we have formulas for the mean and standard deviation of binomials, this means we also can create formulas for the mean and the standard deviation of p-hats. Okay? Now, in terms of what are those formulas, let's talk about it. Okay. All right, for this next part, I'm going to do this from my computer. And hopefully this looks kind of familiar because we were using it the other day, yeah? And do you remember, so we would draw a sample, and here's the sample, and then here's the p-hat from that sample, and then we draw another one, and another one, and notice that the samples change, and it keeps adding the different p-hats down here, yeah? So this is the distribution of p-hats. All right, so we're going to start with, what if my population proportion is pretty low, like I'm going to use like 0.1, and I have a small sample. And I'm going to draw the sample. And in fact, I'm going to draw a lot of samples. Okay, so when my sample size was pretty small, and my P of my initial population is really small, what can we say about the shape? It is skewed right. All right, now, what if I flipped it to 0.9? It is also skewed right, yeah? Everybody good? Or, I'm sorry, it's skewed left. You can see how it's skewed left, yeah? Okay, and do you guys see how they almost like balance each other? And we see why that works. Like if P is 10% success, then you got 90% failure, right? And vice versa, 90% success would have 10% failure. Okay, and heck, you know what I want to look at next? What if P is equal to 0.5? It's definitely symmetrical. The gaps would make me question normality, but ignoring that aspect, this does look approximately normal, yeah? And if I brought my sample size up to, say, 20, that feels a little bit better, right? But is 20 enough to make 0.9 look normal? And the answer is no. Do you guys see what I'm saying here? So a sample size of 20 is great if P is 0.5. It still looks approximately normal. But at P equals 0.9, we're not so comfortable with that, yeah? Okay, but, well shoot, what if I make my sample size even bigger? It's getting closer and closer to normal, yeah? And at P equals 0.5, this looks just great. Definitely normal. I know it's at 0.49, it's close enough. And then if I go to 0.1, looks almost mirrored to over here, yeah. And so it's almost like the bigger like for those extreme values of p, we need a larger sample size to get normality. Are we comfortable with this idea? Okay. So a huge component of what I'm going to be expecting you guys to do on the quest and on your homework is to be able to, given certain parameters, describe what the distribution of p hats looks like. Okay? And when we describe distributions, what are the three things we need to describe? Shape, center, spread. Okay, great. Now, all you need to know about shape is the distribution of p hats will be approximately normal. Okay? And that answer is whenever np and n1 minus p are both greater than or equal to 10. Other ways of saying that, you would expect at least 10 successes and at least 10 failures. Okay? When that happens, this is our rule of thumb that we're allowed to assume that this sampling distribution would be normal. Okay? All right, the center of the p hats. Like I said, there are formulas for this, is p. The standard deviation of the p hats, again, there are formulas for this, is the square root of p, 1 minus p, all over n. I did not put the formula sheet on the quest like I do with your normal tests, but you will be allowed to use your pink formula sheets here. Guys, if you look at the top of this, you can see those exact same formulas. Okay, so I don't expect you to memorize the formulas. You'll be given these. And likewise, you'll be given them on the AP. Okay? Okay, so let's go ahead and flip over to the next page. We have a little bit of redundancy because I've reworked these notes several times and not done a great job of it. Okay, so again, there's a rule, we call it the normal rule or the normal condition. Normal condition is a great way to think of it. And the conditions for things to be normal is that NP and N1 minus P. Think about that P equals 0.9. That wasn't normal because it wasn't, even though NP would have been high, N1 minus P wouldn't. Okay? All right. So let's go ahead and look at this first example. What are some of the important characteristics we might want to note? The 75%. And is that going to be a P or a P hat? P. Lovely. What else? N equals 1,000. Great. And so if I asked you what is the mean of the P hats, you would say, well, what's the formula for the mean of the P hats? Well, it's P, which is 0.75. Standard deviation of the p hats? The square root of p, 1 minus p, all over n. So that would be, 0.75 times 0.25 over 1,000. And I would bet it's somewhere near, maybe a little bit smaller than 0.015.
0.014.
Could you know that because you've done this before, or?
I can tell you in about a month. I can tell you how I knew that.
So you're cheating and you're not revealing your secrets.
Correct. has something to do with a sample size of 1,000 is related to a margin of error, say like in a political poll, being about 3%. And next semester, early next semester, we're going to learn how do you calculate your margin of error. And the answer is roughly 2 standard deviations. So the fact that the sample size was 1,000 told me that 2 standard deviations was about 3%. And it's a little bit smaller because of the 0.75, 0.25. But that's just like one of those things that eventually you guys will be able to think through how I got that answer in my head. You're just not there yet. Nor will you be expected to get to those answers as quickly in your head because you're going to have all these formulas to be able to do all these calculations. Okay. All right. Hey, is the sampling distribution approximately normal? So what should we do? Use the normal condition. I would say n times p and n times 1 minus p. Now, you're not going to like this. I'm not really worried about you not liking it because I'm not the one that sets forth these expectations. You're going to end up having to do this normal condition more times than you can possibly imagine. Even when it's obvious, you need to say what are the 2 values and state what you're looking for those 2 values. So I'm going to need to see the numbers, and I'm going to need to see the greater than or equal to 10. Okay? All right. Now, what would happen to the standard deviation if my sample size was 9,000 instead of 1,000? What do you guys think? Well, what do we know about the standard deviation when it comes to a larger sample size? It should go down. It's definitely going to go down, okay? It's definitely going to go down. The question is, how much will it go down? Can we be more specific? It's not ninefold. Because that 9 that we multiplied by is under the square root sign.
By about
Threefold?
0.004, which, guys, is roughly a third of the 0.014. Okay? So the standard deviation of a sample size is 100% or standard deviation of a sampling distribution. Remember, this is we all take different samples, and all of our samples have different percentages, and we're trying to talk about how different our percentages are from each other. It ends up working out that it's whatever you do to your sample size, you do the inverse square root to your standard deviation. So if you multiply your sample size times 9, the inverse of that would be dividing by and then square root of 9. If I cut my sample size into 4, right? Like if I went from 400 down to 100, okay, so I'm dividing my sample size by 4, my standard deviation would get multiplied by 2. Right? They work backwards from each other. Everybody good? Okay, almost done. Okay. Thoughts? So far, I should say.
E
equal 1.35.
Great.
Sample size is 15.
N equals 1,500. Lovely. Okay. So next. Can you guys determine if the normal condition is met?
So the normal condition, that's just telling us, is it actually just distributed, what the shape of it is?
It tells you if the shape is normally distributed or close enough, approximately normal. So, okay. I just want to point out one more time that the College Board, and therefore me, would expect to see both of these numbers and the greater than or equal to 10. Okay? Students tend to try to do only the lower one and then get mad at me when they get a P. So I'm telling you right now, don't do that. Do both, please. All right. Next, can you guys find the mean? You know what? I'll find the mean. Why don't you guys find the standard deviation?
Zero, one, two. Sorry, Seth.
No, I just thought it was funny.
Say it again. 1, 2, 3.
0, 1, 2, 3, yeah.
Cool. All right. Now the question becomes, what is the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true value? Okay. The idea behind this is if I use 2% as my margin of error, is my sample going to be close enough to the actual value? Does that make sense? Okay. And so if you have all of these possible samples, right? And what we're saying is we know we have this distribution. Whoa. It's mostly the fact that the mean wasn't over the mean.
I always get like the first half good, and then the second half is a lot worse.
Get complacent. Okay. Now, so the basic premise of this, guys, is could I take a sample whose p hat is 0.352? Yeah, that would be this guy right here. And then I could take a different sample whose p hat was 0.341. That would be this guy right here. And then I could take a different one. You guys catch my drift? And imagine each of us gets a different sample. Our p hat's going to be all over the place, yeah? We're going to have some here. We're going to have more of them towards this 0.35, but we could get one this low, right? They're going to be everywhere. Imagine this is a mound filled with p hats. And I want to know, what is the probability that the p hat I get is within 2% of this 0.35? Well, what would it mean to be within 2% of 0.35?
Between 0.33 and 0.36.
It could be as low as 0.33 and as high as 0.37. And if I'm remembering correctly, it's really close to like 90%, 0.896. And you guys now see why I reviewed the normal distribution with you guys. This is going to come up a lot. Okay. All right. Now, we're going to take a 5-minute break.